A single circular linked list, SCLL, is a special type of linked list in which the last node of the list does not point to null, unlike a standard singly linked list, but instead points back to the first node, forming a continuous loop. This circular structure makes traversal different and permits various operations to be performed more efficiently without needing to check for the end of the list. A single circular linked list consists of nodes, and each node contains two fields: a data field that stores the value and a pointer field that stores the address of the next node in the sequence. The last node's next pointer holds the address of the first node, making the entire list circular. To maintain an SCLL, usually a pointer such as head is used to reference the first node. Sometimes another pointer called tail is used to make insertion at the end quicker, but it is optional. Traversing the list requires starting from the head and moving from one node to another using the next pointer. Since the structure is circular, the traversal must be carefully controlled so that it stops when the head node is reached again, instead of continuing indefinitely in an infinite loop. A single circular linked list has several advantages over other linear data structures. Because of this circular arrangement, you can access all the nodes by starting at any point in the list. You do not need to begin at the first node. This property makes circular lists useful in applications like round-robin scheduling, buffering, and systems that require continuous looping. Operations on a single circular linked list include insertion, deletion, searching, traversal, and updating of nodes. Insertion into an SCLL can be performed at the beginning, end, or at any specific position. Inserting at the beginning involves creating a new node, adjusting its next pointer to point to the current head, and updating the last node's next pointer to point to the new node. After that, the head pointer is updated to point to the new node. Insertion at the end requires traversing to the last node, then linking the new node after it, and finally pointing the new node's next pointer to the head. Inserting at any specific position requires traversing the list to the desired location and then adjusting pointers. Deletion in an SCLL also occurs at the beginning, end, or any position. Deleting the first node involves pointing the head to the second node and updating the last node's next pointer to the new head. Deleting the last node requires traversing to the node just before the last, updating its next pointer to point to the head, and then freeing the memory of the last node. Deleting at a specific position requires careful pointer manipulation to maintain the integrity of the circular structure. Searching in an SCLL involves traversing from the head and visiting each node until the target value is found or until the traversal comes back to the head, indicating that the element does not exist in the list. Because the list is circular, searching requires an additional check to avoid infinite traversal. Updating a node's value is straightforward once the node is located through traversal. Single circular linked lists offer much flexibility compared to arrays and normal singly linked lists. They do not require contiguous memory allocation and can grow or shrink dynamically with insertion and deletion, since the last node links back to the first. Repeated traversal becomes seamless in circular applications like multiplayer game turn coordination, CPU scheduling algorithms such as round-robin scheduling, real-time streaming buffers, and problems requiring continuous iteration through elements. Another major benefit is that SCLL avoids the null pointer problem present in singly linked lists. Because no node points to null, traversal errors due to unexpected null values are minimized. However, despite being efficient and useful, SCLL has some disadvantages. because every insertion or deletion operation involves pointer adjustments. Small mistakes or incorrect pointer updates can break the circular structure or cause infinite loops. Searching for a specific element takes linear time, because each node must be checked until the head is reached again. Memory overhead is higher than arrays because of the pointer fields stored in every node. Implementing a single circular linked list requires careful handling of edge cases such as operating on an empty list or a list with only one node. For example, deleting the only node in the list should make the head null, and the next pointer of the node must be carefully cleared. Similarly, care should be taken during traversal so that the loop does not run indefinitely. The circular nature also makes debugging more complex because there is no natural end to signal termination. From a programming perspective, SCLL is frequently implemented using dynamic memory allocation functions like malloc or calloc in C, allowing nodes to be created at runtime. When nodes are deleted, free must be used to avoid memory leaks. In some applications, keeping only a tail pointer instead of both head and tail can simplify operations. If the tail pointer points to the last node, then tail to next gives direct access to the first node, allowing constant time insertion at the beginning or end. Overall, the single circular linked list is a highly versatile data structure that enhances the capabilities of the basic singly linked list by linking the last node to the first, allowing continuous traversal. It supports dynamic memory usage and enables efficient implementation of circular algorithms. Its structure makes it ideal for scheduling, continuous monitoring systems, buffering, and any application requiring cyclic processing of data. Even though managing pointers in an SCLL requires careful attention to avoid errors, the advantages it offers in circular operations make it a powerful and widely used data structure. In computer science, with proper understanding of pointer manipulation, insertion, deletion, and traversal techniques, the single circular linked list becomes an essential tool for implementing advanced algorithms that require circular data flow, flexibility, and dynamic growth.